All right, welcome to Bungalows for Bachelors number 11. Today we are going to be talking about digging and dirt and the dirt that goes under your house and why it's important to have good dirt under your house. So we're going to go ahead, share the screen and get going here. All righty, so we are in phase 2, site development. Today we are talking about excavation and pad preparation. Oh, I gotta get this thing. Oh, there it goes. Okay. So why would you excavate on your property? Well, the main reasons are that you don't really want to build on the soil that's on the top of the ground because it's super unstable. As you see in that photo down there, those some expansion cracks from the soil drying up, and those can go, I don't know, a foot, 2 feet, maybe 3 feet deep sometimes, depending on if you got bad soil. And organic material falls into those cracks and it mixes with all of the soil. And you don't want to put stuff on organic material mixed soil because organic material degrades over time and loses its volume when it's, degrades. So the soil basically shrinks in volume or it settles. So more than it normally would. So that's bad. Um, we also excavate, dig down into the ground with our building foundations because we want to establish some way to restrain the building from sliding around laterally on the ground. It does sound a little silly that would be something to worry about. However, if you have something that is heavy enough and not embedded, the earth is capable of doing some crazy things. So it is a good thing to have. We're gonna have to watch a little video later of that, but it is very important. So the other reasons would be to gain buildable space below a house, like if you need a crawl space or you want to have a basement, then you're of course digging out a lot of soil. And if you have a steep slope on your site and you need to basically do a cut and fill or anything like that, you're going to be excavating for your pad. So what makes soil unstable at the top level? Well, there's your degrading organic material like logs and leaves and stuff that doesn't crack, stuff like that. The plasticity index is naturally higher in the top layer of soil. The deeper down you get into the soil, the more stable it is. And I'm not entirely sure why that ends up happening. I'm not a geotechnical engineer, but I do know that deeper soils are generally more stable. And that's not necessarily because they get less moisture or less sunlight and things like that, but it's like the actual plasticity index drops the deeper you go. Not sure. And of course, once you hit bedrock, then boom, boom to yada, you have no PI. So, and the other thing that makes soil unstable is if you're in a sandy place, then you are going to have a crystal realignment problem sometimes. Basically, what happens is if you put something on sand and put weight on it, like if you're walking on a beach, the sand is not going to fall out of place under your foot. Now, if you've ever taken your feet and walked over to where the waves are coming in and you've stood, not necessarily in where like the waves are happening, because that's like an erosion thing, but let's say the sand is saturated and wet. And if you start shifting your weight on your feet and you're moving them around, you will sink into the sand. And the reason that's happening is because every time you move, the water is allowing the crystals to realign. And when it does that, you can drop down deeper into the sand. So building on sand can be actually quite stable because there's no PI, plasticity index, but you got to watch out for water problems because it can be equally as bad. So that makes soil unstable. So what could possibly make a house move laterally? There goes the screen. So steep grades can do this. If you build a house on a steep slope and you, for whatever reason, don't bench your beams, bench cut as in like all of your beams are sitting on the ground flat. You don't put a sloped beam on the ground. Like you wouldn't do that because it could like slide down the dirt. So what happens is you step all your beams or you step your changes in elevation. So you're flat, step up, flat, step up, flat, step up. And that keeps things from sliding around down a slope. Wind loads, winds can get kind of crazy, and winds are capable of producing huge lateral forces on houses. Now, houses are quite heavy, so there's a lot of friction in the ground. So, not a lot of embedment wouldn't be a huge deal here. However, seismic loads are capable of doing much crazier things. And the seismic loads shift the house back and forth very quickly. So when your house is not embedded properly, that would be a scenario where you'd have a serious problem. So we are going to watch a quick little video that is taken from summaries of people who, let me make sure that it's popping up here. It says sharing screen, but it's not sharing. Make sure it's, there it goes. So these are shake table tests, where they basically take houses, they build them on a huge shaking table, and then they shake them and see if they fall down. And this is just an example to show you the kind of craziness. I don't know how well this video is going to come through, but you can always go back and click on the link if you really want to see this, or just YouTube it yourself. But the basic premise is they shake houses, they shake buildings to test. They have sensors everywhere, and if your house is not, at the very least, properly secured to the ground with embedment into the soil, then you're going to have some sliding problems, and it's not going to be a good day. And we're going to talk a little bit about what happens if you have rock and you don't want to embed into the rock in them at the end here. But these are just some examples. So houses can shake and fall. We want them embedded in the ground so they're nice and sturdy. So when you want to gain volume below grade for basements and crawl spaces, then you pretty much just dig out for whatever you need to build a little bit outside where your foundation is going to go, so you can properly build walls and things like that, and then properly waterproof those walls. But that's a very basic premise there. When you are doing cut and fill, then you want to, of course, dig out the part that's for the cut. And then when you're placing the grade for the fill, you wouldn't just cut out the natural soil and scoot it over and dump it where you want the fill. You should probably get properly, I mean, unless you have very nice cut dirt, you wouldn't want to dump that. You'd want to bring in structural fill and build that and compact that up. We'll talk about pads in a second here and building up pads, but that's the basic premise. Let me go back here, previous. One of the worst cut and fill cases I ever saw in my engineering past was a property that was being developed for a bunch of duplexes and a huge apartment building at the back of the property. The back of the property was super steep, grades in like 5 to 10%, and it was covered in oak trees. So basically what developers like to do to maximize, I mean, they need to maximize buildable area, because the more stuff they fit there, the more money they're making and the more price per area of property they're getting. So they want as much space to build as possible. And usually you build space by doing cut and fill, so you can have more flat buildable space, right? So at the back of the property where it was super steep, the guy basically knocked all the trees down, and then on all the trees on the rest of the property too, and he just pushed everything to the back of the lot in a pile, trees, logs, stumps, you name it. And then he just covered it in dirt, and he filled the whole thing up. And this guy wants to put a massive apartment building on top of that, basically. So we left that project. The project did not end up happening, but basically, hopefully nobody ever builds on that, because that stuff's going to sink like multiple feet probably at some point, and hopefully nobody builds on it. But yeah, that was a mess. So don't cut and fill like that. Use good fill. So why would you want to control potential vertical rises, PVR, and PI's plasticity index? Well, because houses are basically boats that you're building on land. The land can move up and down in different places, and it can shift around. So if your foundation is not strong enough, then you're going to have flexing in your house. Now, most houses, if they're built to regular standards, the houses are going to flex enough to crack sheetrock, possibly crack foundation, and it can still be within allowable tolerances for structural safety, because our code does not have very stringent standards. So there are two types of design for houses and foundations in this regard. There are designed for safety and structural capacity, and there's designs for serviceability, which is what it's called. Serviceability is more about making sure things look good. So you can design a wood beam in your house to not break, or you can design it to not bend so much that it doesn't look like your ceiling is bending and bowing. They're two different limits. So most houses are built, unfortunately, to the safety standard, the minimum, and foundations crack, sheetrock cracks happen. So if you want to go above and beyond with the foundation, then you can resist this tendency to happen. But a lot of times, even with crazy foundations, sometimes it happens anyway. So it's just kind of the only way to avoid this problem is to put your house on bedrock. And that's the best probability you have at success of not moving at all. So that's what you ought to do. So when you're doing building pads, the basic process, of course, would be that you import your structural fill. which is going to be a soil that has an extremely low to no plasticity index. It's going to have a lot of good, it's going to have good tackiness. It's going to stick and compact well, and it's going to have good rocks in it for structural holding weight. So you're going to import special dirt, and then you're going to place that dirt in lifts, and a lift is referred to as a layer. So you don't want to just dump it all out where you want it and then try to compact it, because you're not going to be able to basically compact the dirt to a high enough density to properly support it down deep. If you pour 2 feet across the ground, try to compact it, even with a heavy compactor, you're not going to be able to compact the dirt at the bottom very well. So the normal rule would be 6 or 8 inch lifts if you have heavy compaction equipment. But a good safe rule is like a 4 to 6 inch spread. You can basically wet that soil and then compact it, and it will be quite good. And in most cases, it's a good idea to compaction test if you're going to be putting the weight of the house on that. That will be a time to know that it's good and compacted. The house picture here is a situation where they most likely prepared this pad, compacted it to probably 95%, and then they just let it be. They trenched the beams for the foundation out straight into the soil. They did not worry about burying the weight down into the natural soil below the pad. Sometimes it's a good idea to get support from below the pad, which is what you see in the bottom. You can put these piers in at the intersections of the beams and basically support the house on the soil that's beneath. So various ways to do it. There have been cases where somebody builds a pad and they don't know how to build a pad. So they just basically dump a bunch of soil and drive on it and say it's compacted, ready to go. And they get a geotechnical report done and it's super loose. So instead of redoing the pad, they basically have to put in piers at all foundation intersections and corners down to a proper depth in the original soil to support the house, which just costs way more money. So it's kind of a losing situation there. But that's why you build pads correctly. And let's talk, let's go back here. So a little bit about, oops, good job, Sam. A little bit about the amount of soil. So this has to do with the potential vertical rise. I didn't explain that. So potential vertical rise is a geotechnical term for what is the potential for the soil to rise, basically. And it sounds complicated, I know, but it is somewhat simple. And they basically do a bunch of math, and they have equations for what type of soil is it, what is the plasticity index of those soil, how deep are the layers in that one place. They take a coring sample to know, 6 inches of this, and then 8 inches of that, and then 12 inches of this, and then 6 feet of this. And they combine all this information to tell you that you basically have this potential vertical rise of some number. Now, maybe it's initially 6 inches if you're on bad soil. What that means is seasonally, when it's dry, you could be down 6 inches, and when everything's wet and expanded to its fullest saturation point, you're going to be up 6 inches. So that's a lot of movement. If you have varying dryness and moisture around your foundation, that can be huge movements, and that can very definitely stress your house, and you don't want that. So basically, geotechnical engineers can prepare a report that tells you, hey, if you remove below your foundation 3 feet of natural soil and you put in 3 feet of structural fill properly compacted at 95%, your potential vertical rise will be this. And usually in a report, they'll give you maybe 3 cases where they say, all right, if you remove 5 feet, you get this. If you remove 3 feet, you get this. Remove 1 foot, you get this. And basically, the more you remove and replace, the more stable your foundation is going to be. But of course, that costs more money to remove, export the dirt, yada, 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 import new dirt, stuff like that. So usually for residential purposes, unless you have a very expensive home, people are not ordering geotechnical reports. They are just getting soil tested for its plasticity index, and then an engineer is going to basically give a reasonable size beam to handle that dirt. Depending on how things are normally built in a certain area, for example, in San Antonio, most homes are just built on the natural soil with big beams. They're just strong foundations. They're designed to withstand the bad soil. If you're in College Station or Temple, I believe the standard is more so to build up good pads with structural fill that are compacted, and then they trench into those pads to basically just put the house on the better soil built up off the ground. So there's just 2 different ways of doing it, and it just depends on what's normal in the area. If you're in an area where they're building up pads like this it's probably going to make the house more expensive, but the house is naturally going to have a better lifetime, better stability on that soil. So when the bottom of the foundation beams are bearing on good fill, maybe a foot to 3 feet, and then you have the bad dirt, you're much more likely to have a stable foundation. So that's what the potential vertical rise thing is about. In commercial buildings like Walmart's, gas stations, that stuff like that, you're going to see way more of this careful soil treatment. You're going to see a ton of over excavation where they dig down deeper than they need to, and they come back and they fill it up with good compacted structural fill so that this crazy huge building doesn't have bad soil problems. It's much more important. This is not a commercial buildings don't mess around with foundations. Okay, we had some technical difficulties there, and we're going to go ahead and finish up this lesson. The 3 stories that are going to be on the screen, I'm going to freeze it and show it over this recorded version and talk about it while I'm doing this. So these 3 photos are showing the 3-story house in tree mode where it's got nothing cleared and it's got all the trees cleared in the next photo, and they're starting to put the forms up for the foundation in the 3rd photo. So when you have a foundation that has rock right below the surface of the dirt, and you don't want to jackhammer the rock for the trenches to get your embedment in the soil, then you can dowel into the rock with rebar. Basically what you do is you just drill a hole, and then you epoxy the rebar into the hole so that it can't come out. And you just do that all around the foundation exterior, the perimeter beam. You don't have to do it on the interior beams. And you make sure that basically that rebar is sticking up so that when your foundation's poured, the concrete has been connected laterally to the rock so it can't slide around. So that's how you get out of that one. And for some extended understanding, you should watch first of all, you should just watch the whole Spec House series by Essential Craftsman in general, but specifically related to excavation and pad preparation, you could watch episodes 1 through 3, 5, 7, and 25 through 28. I'll go ahead and take a screenshot of this and put this up on the screen for the post-production video, but for now, I will just talk about it. And then watch a YouTube video, Why Does Road Construction Take So Long? By Practical Engineering. That video talks a lot about basically the premise of compaction and how much dirt is moved in 6-inch lifts and all that stuff. So those are the 2 videos you could watch to learn a little bit more about this topic. But that is going to end it for BFB number 11. We will see you on the next one.